Yeah. Let's go. Yeah. Okay, Lebesgue measure, Lebesgue integral is defined to be, so we have this measure space, x, by x I really mean x measurable sets and a measure. The Lebesgue measure was defined to be like this, and then what we proved was that this is independent of representation. So it doesn't have to be a canonical form, could have just defined it as any representation. What else did we prove? We defined in general, so if x, again, non-negative, may be extended, is measurable, then we defined its integral with respect to mu to be the supremum over all simple functions bounding f of these integrals. Yes? Then we showed the monotone convergence theorem. Monotone convergence theorem. Let's do the real version. So if the fn's are non-negative and the fn's are increasing and the fn's approach f almost everywhere, then the integrals of the fn's converge to the integral of f. Okay? And then we derive some consequences of this. Consequences, or corollaries. We prove that if f is non-negative, then the following two things are equivalent. The integral of f being 0 is equivalent to f being 0. Almost everywhere. We proved that if fn's are non-negative, then the integral of the series of the fn's is equal to the series of the integrals of the fn's. Yes? We proved Fatou's lemma. Slide things up. Fatou's lemma that, again, if the fn's are non-negative, then which way is it? Where's the lim inf go? Inside the integral or outside the integral?
Integral limit of the integral is outside of.
Yeah, so if you can't remember,
ILL.
ILL?
I integral limit integral.
I see. That's a mnemonic. Okay, we can go with mnemonics. So I just remember by taking two functions. So there's f1, which has values 1 and 2, and then there's f2, which has the values 0 and 3 or something. 0 and 3. And so the sum of these, so the integral of f1 is equal, let's make it, has the values on 0 and 1 or something, with measure giving half mass to each. So the integral of this is 3, the integral of this is 3, the integral of f2 is 3, right? But if I take the infimum over both of these, so the infimum, which is the lim inf of the f's, is 0 and 2. So the infimum always has integral at most. So Fatou's lemma is lim inf of the integral of the fn's is at most the integral of the lim infs. Did I do that right?
I see 0.
0 and 2. So the two values, this is the pointwise lim inf.
Oh, I see.
Which is a pointwise inf, because I just have 2. So if you just check it on two functions, I just made the smaller value at different places. And then here it's 0, here it's 2, so the integral of the infimum is 2. So the integral of the infimum is smaller. Did I do that right?
So now what you have is what you wrote last time. I think.
Okay, let me check. The integral of, yes, this is correct. This is correct. What's your mnemonic? All right, let's see the mnemonic.
ILLI.
ILLI. But how do I know where to put the less than sign? Or it's a less than sign.
Integral, then the limit. And then,
Integral then the limit.
So.
Oh, integral then the limit is less than limit and then the integral. Fine.
Yeah.
Well, the less than sign is like, it's the better sign.
I guess so. So this will say the integral of the lim inf of the fn's is at most the lim inf of the integrals. I. Fine. But if you don't like mnemonics because you don't remember them, all you have to do is try one function, one pair of functions, and then you see which way it's going to go. Okay. Let's do a quick variation on this. It's kind of like when sets increase, their measures increase. If sets decrease, their measures decrease as long as one of those measures is bounded. So here's a reverse Fatou. Reverse Fatou is, again, the fn's are bounded, and there exists a g with integral of g finite, such that the fn's are bounded by g. Then, the same thing except in opposite holds with lim sups. Then, so now I really want to say the lim sup of the integrals of the fn's is bounded by the integral of the lim sups. You got a mnemonic for this?
It's actually the same one, because the I also would apply to the
But
soup,
that-
but then Li would apply to the soups. Because intro then limit for the ints, and then for the soups. Because lim sup bounds lim inf as well. So you have all the inequalities that you want. But it's mnemonic.
I definitely have.
Because you have lim inf, but the integral is less than or equal to the lim sup with the integral.
But now the limit is on the
Yeah.
side on the right.
Yeah, but you have the limit on the right, the second L. It's for the second lim sup. For the first lim
Anyway.
sup.
Okay, so if you you can have mnemonics or you could just think about it for a second.
Can you scoot over for a tiny bit?
Sorry,
Okay,
reverse for
I
two.
just was wondering if there was something over there. But
Reverse for two.
Okay.
Yes. How do you prove reverse for two?
You use regular for two, right?
You use regular for two on
On the negative?
G minus f. That's the whole point. G minus f is non-negative, and so you use for two. So the integral of the lim inf of G minus fn's is less than the integral, the lim inf of the integral of G minus fn's. This is a lim inf. I don't have room to write inf. Okay? And so but the lim inf of G minus fn, this is equal to G minus lim sup of the fn's. And the integral is linear. And same thing here, the limit of G minus fn, but each of these is the integral of G minus the integral of fn. G doesn't depend on n, so it pulls out of the limit, and then the integral of G was finite, so I can drop it from both sides, and this inequality goes to the other side. Does that make sense? You need me to write more, or you can do the rest of the algebra. This is elementary now.
Okay.
Question?
Is this lim
So this is a lim inf,
yes.
and the point is the lim inf of G minus fn is equal to, G is a constant, lim inf of a constant is just a constant. So lim inf of G minus fn is G minus the lim sup of the fn, because when you pull a minus sign through an inf, it turns into a sup. And then you cancel the integral, so then you integrate on the outside. You cancel the integral of G because it's finite. And then you move things to the appropriate side. Okay. Anything else? All right. I think that's as far as we got. Do we even do reverse for two last time? No. Okay, but now we have. It's one That was integrating non-negative functions. So if you have a real valued function, how do you integrate it? Split it into plus and minus. F plus is the max of f and 0. F minus is the max of negative f and 0. So f is equal to f plus minus f minus. And then we say, so if the integral of f plus is finite and the integral of f minus is finite, then we say the integral of f exists, integral of f exists, and is equal to the integral of f plus minus the integral of f minus. So the plus parts and the minus parts must both be separately integral. Or alternatively, I mean, this is equivalent to the integral of the absolute value of f, which we know how to integrate positive things being finite, because the absolute value of f is
F plus
f plus plus f minus. Okay? So the integral of a function exists. By that I mean the absolute value of the integral exists, in which case we can split it up, and its value shall be defined to be the plus part minus the minus part. What if we want a complex valued function? Exactly. You take so f is equal to real part of f plus I times the imaginary part of f. These are two real valued functions. And so I again want to know, so if the integral of the absolute value of f is finite, then I declare that integral to be the integral of the real part plus I times the integral of the imaginary part. And this happens if and only if the integral of the absolute value of the real part is finite and the integral of the imaginary part of f is finite. And why is that?
It's a kind of like a triangle inequality.
It's a kind of triangle inequality. So if you have a complex number z, its absolute value is at most, so here's the complex plane, and here's a point z. The length of z is at most the real part plus the imaginary part. Each one individually is, of course, also bounded by the absolute value of z. So this is bounded by twice the absolute value of z. Okay? So this integral is bounded above and below by constants times the sum of these two integrals. So for it to converge, both of these must converge and conversely. Okay? So once you know how to integrate positive functions, you know how to integrate complex functions. As long as they're integrable. Good. Yeah, I think if I get a marker, a lot of people will be happier.
It's only the corner that is not. It's
That top
yes,
corner.
Yeah, that top one.
The top corner is always bad.
But
Wonder if there's smudge on here or something. Okay. All right. So let's talk about the space. So definition. This is a preliminary definition that we're going to fix in a minute. The space L1 of x mu, and you can stick in M if there are other sigma algebras floating around, is the set of all functions. Well, depending on what you want, typically you take this to be a complex vector space that are measurable, that are integrable. Integrable. So measurable and integral. Integrable, I mean, of course, that this integral is finite. Okay? This is a vector space. This is a vector space over, well, whatever we want it to be. But over the reals over the complexes. Why? Is the 0 function integrable? Yes, if two functions are integrable, so 0 is in L1, f and g are in L1 implies f plus g is in L1 because triangle inequality, and it implies that any constant multiple of f is in L1 because the integral is linear. Okay, so it's a vector space. Okay, so here's a theorem. So let me give you some general theorems about the structure of integrable functions. Let me slide up a little bit. General theorems about the structure of integrable functions. So the first is, let's put it this way, f has small tails. Integrable functions have small tails. So if f is in L1 and x is sigma finite, so there's a countable collection of measurable functions, measurable sets with finite measure whose union is x. Then for every epsilon, you can see that, there exists some measurable set with finite measure such that the integral of f over the complement, and I can even take the absolute value of f over the complement, is at most epsilon. If you're integrable and x is sigma finite, so here's x. If you can integrate f on all of x, then there's some set E, so that outside of E, the integral of f is at most epsilon. Question?
And then in the real case, this can be E can be taken to be like a ball.
Balls.
Or...
Yep. G, x equals RD, E equals big enough ball. Ball about the origin of size n, for n large enough. Let's prove this. Okay, first of all, may as well assume the only statement is about the absolute value of f, may as well assume f is non-negative, real and non-negative. Assume f itself is non-negative. Let x be the union of some countable collection of sets with the measure of each being finite. We assumed it's sigma finite, so we can do that. Then we're going to make a sequence of functions, and I'll make the ENs increase. If they're not already increasing, just take something that's the union of the first n of them. And En is contained in En plus 1. Then we make a sequence of functions Fn, which is f times chi En. F is non-negative. The chi's are 0 or 1. They just chop you down, but they chop you down less and less. So the Fn's increase to f. Since at the end of the day, every point of x is captured by one of the ENs.
Can we always find such a union?
So I'm assuming that x is sigma finite.
Oh, that's
I'm assuming that these ENs exist. Yeah. Okay? So I'm going to apply the monotone convergence theorem that tells us the integral over Fn converges to the integral of f, and the integral of f is finite. And of course it converges from below, since the functions converge from below. So for every epsilon, there exists an n so that the integral of f minus Fn is at most epsilon. But this, the integral of fn is the integral of f over en. And so this is equal to the integral of f over en complement. Which is exactly what we were trying to prove. Take E equals En.
So what goes wrong on a non-sigma finite space?
Well, if I can't have Fn necessarily converging, if I can't cut F into things of finite size and have it converge as I go all the way out.
Right. So the argument certainly fails. Does the simple result hold nonetheless?
You can come up with so first you have to come up with a non-sigma finite space, which isn't hard to do, but it's something that is annoying.
Okay.
And then you make a function on that thing, which converges in some nasty way that no matter what finite sets you take, no matter what finite measure sets you take, you're still missing some positive proportion of the integral. Okay, let me leave that as an exercise. Is it an exercise? Am I giving away exercises? That's not an exercise, as far as I recall. Okay, the other one I am giving away. Well, not yet. Okay, so this is just saying if you have an iterable function on a sigma finite space, the tails are small. Let's do another one. Let's prove the absolute continuity of the integral. So here's a theorem. If f is in L1, then for every epsilon, there exists a delta, so that for all measurable sets with measure at most delta, if I integrate the absolute value of f on that set of size at most delta, I will get at most epsilon. So this is the absolute continuity of the integral. Absolute continuity of the integral. We'll get to the significance of this later. Question.
So in particular, the integral from minus infinity to x, if you make that a function of x, is absolutely continuous, or is uniformly continuous? I haven't read this.
Wait, this can't be a homework question.
It's related, apparently.
It's related to a homework question. Good.
It gives a trivial answer.
But that, well, I would say the previous one is more related to minus infinity to x. Because this minus infinity to x doesn't have measure at most delta.
You take the difference.
You take the
So I don't know what the
x
question.
and x plus.
What's the exercise?
I haven't read the exercise. I was just asking you a question.
Okay, it's something about absolute continuity.
No, uniform.
Uniform continuity. Okay.
So when you do that, you get the.
All right.
Okay.
So let's talk about exercises in office hours. But this is an easy thing to prove. I'm foreshadowing what we'll be talking about when we talk about the fundamental theorem of calculus, which requires the absolute continuity. But the integrals are absolutely continuous, and functions that are absolutely continuous are ones that satisfy the fundamental theorem. Okay, so once again in the proof, there's no reason to take anything but a non-negative function. Take f non-negative, and let E sub n be the set of x on which f of x is at most n. Okay, these are again increasing. I know that f is integrable, so it can't take the value infinity on a set outside a set of measure 0. So these might not cover all of x, but they cover all of x that you would need to integrate over. Okay, and let f sub n be f times the indicator function of x of en. In other words, it's what we did when we were constructing simple functions. It's part of what we did when we constructed simple functions. If I get above n, I truncate, cut off at height n. Okay. These increase. They increase to f almost everywhere. Not the places where f has value infinity, but those have measure 0. So again, I will apply monotone convergence, left, right, center. And what does that tell us? The integral of f over these chi ens, which is fn, the integral of fn's, converge to the integral of f, which is integrable. So there exists an n, so given epsilon, there exists an n so that the integral of f minus fn is at most epsilon over 2. So far, so good. What are we heading for?
So what does that say? The last integral?
This is the integral of f minus fn.
Thank you.
Right? This integral goes to this one, so the difference, and this is always smaller, so this is a positive thing. The difference can be made arbitrarily small by taking n sufficiently large. And now we're going to pick delta. So once we have this value n, given epsilon, we pick delta to be anything smaller than epsilon over 2n. And now assume that we have an arbitrary set, measurable set, has measure less than delta. Let's look at the integral over e of f. This is what we're trying to bound. I do nothing by subtracting fn and adding fn. Let me increase the domain here. This is a non-negative function, so if I increase the domain, I only make it bigger to be all of x. The value of fn is at most en. Is at most n. The value of fn is at most n, so this is n times the measure of e. This is epsilon over 2. This is n times delta, which is at most epsilon over 2n. Okay, absolute continuity of the integral. Very good. All right, so we're getting through kind of the big stories of the integral. First of all, integral has small tails. Second of all, the integral is absolutely continuous. Third of all, this is one of the big three with Fatou and, oh, sorry, some people are still copying. Sorry? Dominated convergence, yes. Yes, you can see where I'm going. Dominated convergence theorem. Any questions on absolute continuity? Dominated convergence. Okay. If I have a sequence of fn's that are measurable, not non-negative, they converge to some f almost everywhere, complex valued for all I know, but there's some integrable function which dominates all of them. In particular, g is not negative. And it's integrable. G is in L1. Then, a couple of things. All I know about these fn's is that they're measurable. They converge to some measurable function almost everywhere.
Is this bound for fn everywhere or almost everywhere?
Almost everywhere. For every n
for every n.
For every n, this holds almost everywhere.
Okay. Could it just be for eventually for n?
What do you mean eventually for n?
For big enough n?
No.
Well, if you want to then just drop.
I think you can just cut off the first part.
Yeah.
Exactly. So almost every.
Okay, so almost every means different things in different contexts. It's true that in number theory, oftentimes we say for almost every prime, which means for all but finitely many primes. But in terms of integers, there's a notion of density. There's a notion of logarithmic density. There's a notion of Dirichlet density. So let's just make that. If you're in a situation where this happens after a finite time, you know what to do, right? Chop off a finite. So first of all, f itself must be in L1, and all the fn's are in L1. And this almost everywhere convergence, if it's with a auxiliary dominated function, then the convergence is L1. What does it mean for two things to converge in L1, i.e.?
The difference in the absolute value.
Yes, the difference of the absolute value has an integral which goes to 0. And by the triangle inequality, and hence the integral of fn goes to the integral of f. So far, so good? Okay. Let me start this up. Proof. All right. So, first thing I want to remind you of, the fn's are measurable. They converge almost everywhere to f. That means that, so we saw long ago that lim sup and lim inf are measurable. Measurable. So f is measurable. That's just reminding you of this. Also, each fn is bounded by g, and f is the limit. So f is bounded by g. So the integral of f is bounded by the integral of g. So f is not only measurable, it's in L1. That's the trivial part of the argument. Very slightly non-trivial is, let me put it this way. So if fn is at most g, almost everywhere, then let's look at f minus fn. F minus fn is at most, well, let's do something really crude.
So are we using equals in the absolute value of f? In f, absolute value of f should be minus
Yeah.
or equals, right?
Thanks. So this is at most 2g. And 2g is integrable. Okay? So now let's apply Fatou in two different ways. So one thing this says, so we have fn, f minus fn is bounded by 2g. And 2g is integrable. So we have reverse Fatou. Reverse Fatou, which we can, let's see, sneak in here. Reverse Fatou, if we have a sequence of non-integrable negative functions and there's an integrable g that bounds all of them, then the lim sup of the functions is at most the lim sup. So the reverse Fatou tells us that the lim sup of the integrals is bounded by the integral of the lim sup. Which is 0 almost everywhere. This is a pointwise lim sup, which is 0 almost everywhere because the fn's go to f. That's dominated convergence. The lim sup of this, in other words, the lim sup is bounded by 0, so the integral, so they go, the fn's converge to f in L1.
Since it has to be non-negative.
Since it has to be non-negative, what has to be non-negative? I mean, this integral, yes, this integral, yes, this lim sup is non-negative, so this lim sup is 0, and so the integral is this. Lim inf is also non-negative. Lim inf equals lim sup equals 0. And hence, the integrals converge. Okay? All right. With these things in place, I think we can get to Reisz-Fischer. Yes. All right, so let's develop things up to Reisz-Fischer. So we have dominated convergence, we have Fatou, as you can see, very useful. We have monotone convergence, we've used it like every proof. So let's talk about the correct definition of L1. So we want, you remember the definition that so this is definition. L1 originally was just the set, it's a vector space, integrable functions, and that's all we said about it. It'll be very convenient to make a slightly fancier definition for a very good reason. So the real definition, here's what I want to say. Well, let me just state the theorem instead of beating around the bush. This is the Reisz-Fatou theorem, Reisz-Fischer theorem. It says that the L1 of x mu, properly defined, is a complete metric space.
And that requires you to take equivalence class.
That requires you to, first of all, what do I mean by metric space? Well, I have a norm. So let's work our way up to this. To make it a metric space, there are metric spaces that aren't norms, but we can go much better. It's a normed space. The metric here comes from the norm. So the L1 norm, which we'll write as this. Question?
Is there a relationship between taking lim sups and the Cauchy sequences, the x and those terms? Who use that?
So that's what we're going to prove is, so what do I mean by it's a complete metric space? The distance function, so let's start with the norm. The norm Fn, the integral of f d mu. And is this a norm? So I need the triangle inequality. That's satisfied because of the triangle inequality. That's a thumbs up, not I'm out of range.
Yeah,
I need the non-negativity. That's true because this is non-negative. And I need to be a norm, I need that the integral is 0 implies f is 0. Which is not true unless we say almost everywhere. Okay? So this is need this for taking L1 to be a norm. Okay? So the real definition of L1, L1 x mu, is, again, the set of all functions from x to, let's say, c, with finite integral up to equivalence, where f is equivalent to g, if and only if f minus g is 0 almost everywhere. The yoga is L1 functions do not have values. I'm sorry to tell you, ladies and gentlemen, you've been thinking about functions as from x to c or something. There's no such thing as f of x. There's no such thing as f of x. So really, when I say f, if I say f is in L1, what I really mean is that there's an equivalence class of all the functions that agree on except for sets of at most measure 0.
And their equivalence classes are determined by what their intervals are, right?
Well, they're determined by if you take the difference and you take absolute values and you integrate, you get 0, which is equivalent to their.
Oh, that's not equivalent though, is it? It's just like what you said is what the definition. What I said follows from the definition.
Well, you said yes, follows. So, yeah, of course. Let's write this down. I mean, does not imply that f equals g almost everywhere, unless f and g are non-negative.
Right. Right.
Okay.
Yeah.
You could still have non-negative functions which just have integrals from different places, right?
Yeah, that's what I mean.
Okay.
So the integrals being the same does not mean that they're the same almost everywhere. Yeah. I mean, that's just
Okay. No.
yeah, not true, and it's trivially so. Take any function with positive and negative values as integral of 0, right? But it is true when these things are non-negative, and it's true not exactly, not point-wise, but almost every. So from now on, when you write f of x, it's a lie. It's a convenient lie. You can think about f of x being a complex number, but it's not a complex number.
You can take a representative.
You can take a representative. That's right. You can work with representatives. Okay? So we'll have theorems about continuous functions, for example, being dense. So you can't say every L1 function is continuous, but you can get very close to one that is. And then you can speak about its values. Because it's hard to move them without breaking continuity. Very hard. Okay? So L1 functions do not have values. Once we have a norm, we have a distance. So we have a metric. So the metric, L1 metric, what's the distance between two functions, by which I don't mean functions, but I mean equivalence classes of functions up to almost everywhere. The norm of f minus g. And again, this will only depend on the values of f and g almost everywhere. Okay? This is a metric. Just like any norm induces a metric. And so this Reisz-Fischer theorem, Reisz-Fischer says the following. If I have a sequence of fn's in L1 that are Cauchy, if this sequence is Cauchy, i.e., let's remember what that means. For every epsilon, there exists an n, so that for all n and m, at least n, the L1 norms differ by at most epsilon. The L1 metric measures the distance epsilon between them. So you just have, this L1, it's an infinite dimensional vector space. It's defined by taking this huge space and modding out by another huge equivalence relation. And you're supposed to find something that it converges to. Question?
Wait, you're saying it's a complete metric space, right?
Yes.
Didn't we say in class that complete metric spaces have small cardinality at some point?
Cardinality at most a continuum.
That's so...
That's, yes.
That's weird.
Yes, this LP space, this L1, has cardinality at most. The continuum is a giant cardinality.
But it's a lot smaller than you would think for functions.
You might naively think that function spaces should be way, way bigger.
I'm guessing there's no basis.
Well, there's always a basis.
Not for infinite dimensional vector space.
It's an infinite dimensional vector space.
I know, but like the basis isn't guaranteed.
That's asking a choice. I
What the entire use of the Reisz-Fischer theorem will be to solve the problem on the very first lecture about what kind of functions are limits of trigonometric functions. This solves Fourier analysis.
Right.
Sines and cosines are a basis for L1 of
That's great.
0, 1.
Right, but am I right in thinking that infinite dimensional vector spaces don't have base?
In general, yes. So general Hilbert spaces that are infinite dimensional, yeah. It depends.
It's equivalent, right?
If you use the axiom of choice, yeah.
Who doesn't?
Yeah,
But-
sure.
Okay, we get, yes. We've been using the axiom of choice left, right, and center. Fine. So here's the thing. You have these functions. Somehow you're supposed to, out of them, find one function that it's then, right? What's the conclusion? Then there exists some integrable function such that Fn converges to F. Of course, the convergence is in L1, i.e. Fn minus F goes to 0. Okay. Yeah, I said I wouldn't do your homework for you. So I was going to show how this is not true if you ask for almost everywhere convergence. So L1 convergence, so it is not necessarily true that Fn goes to F almost everywhere. But I guess since that's homework, let me not do it. I'll save it for office hours. It's such an easy example, and it's very fun. And it's instructive for the proof we're about to give. No, I think I have to give it. All right. Counterexample to almost everywhere convergence. It's very standard. To almost everywhere convergence. Well, you still have to write up your homework. There's a standard counterexample. Here's F1. Counterexample to almost everywhere convergence, even under L1 convergence. So you take the indicator function of the interval, and then you take the indicator function of the half interval, and the indicator function of the other half. Then you take the indicator function of the quarter interval, the next quarter,
So
next quarter, you see what,
Okay.
okay? Half to 3/4.
So this isn't exactly the exercise, but it's good
Yes.
enough to extend to the.
Oh, and you-
Okay, good. Then there's still something for you to do, and so on. So Fn takes infinitely many values of 0 and 1.
So it doesn't converge anywhere.
Doesn't converge anywhere. So for any x in 0, 1, Fn of x is 0 and 1 infinitely often. So no limiting function. No limiting function almost everywhere. Everywhere. Okay? But in L1, the Fn's converge to the function 0 because the integral of Fn minus 0 is the indicator function of these intervals, and the first one has length 1, and then they have length 1/2, and then 1/4. So what's going on is that you have to jump around to find the places where you have convergence. In fact, what is true, and we're going to prove this in a second, I think, what is true is that there'll be a subsequence along which you do have almost everywhere convergence. So on the subsequence that takes 0, 1, and takes 0, 1/2, and takes 0, 1/4, and 0, 1/8, you have convergence except at 0 to the 0 function. Okay? So it'll be very important to take, it was important to give this away because it'll explain why we're going to do what we're going to do in the proof. So you have to speed up the convergence. The initial convergence might be very slow. So slow that you don't get almost everywhere convergence. But when you speed up the convergence, you do get almost everywhere convergence, and then you get L1 convergence. So let's do that. Any questions? So this doesn't, so what was the homework? It wasn't this?
You have to do it over
That's exact.
all of R, and then you have to extend it to RD. But
Okay, I gave it over. That's okay. So here's the proof. Okay, so again, we have this sequence. We know that for every epsilon, there exists an n, so that for all n and m bigger than n, in L1, the difference is at most epsilon of this sequence of measurable functions. Okay. Step 1 is to speed up. Exactly because of this counterexample, we need to speed up the convergence. So take epsilon equals 1 over 2 to the k. So there exists some n, let's call this nk, so that for all n and m greater than nk, fn minus fm is at most 1 over 2 to the k. That gives us a subsequence. So f and k is a subsequence for which, in particular, applying this to nk and nk plus 1, fnk minus fnk plus 1 is at most 1 over 2 to the k. Okay. So now we're going to define some functions. So let's go straight to f of x. Let f of x be the following function: f and 1 of x plus a sum, as k goes from 1 to infinity, of f and k plus 1 of x minus f of nk of x. What's going on? Why have I defined this thing? Let's look at its partial sums. Look at f k of x, which is the same thing, but cut off at, let's call it k minus 1. As you already saw, or some of you already said, it telescopes. So n1 cancels out n1, and n2 cancels out n2, and so on, up to the only thing that's left is when k minus 1, I get here at k plus 1. This is a little k, of course. Exactly. This is just f and k. So the partial convergence of this thing, if you truncate that infinite sum, you're just recovering f and k every time. But each fk is bounded by gk pointwise. Again, there's no such thing as pointwise anymore. It's almost, and whenever I say pointwise, I mean almost everywhere. Where gk is equal to these finite sums, just with absolute values. Or take a representative so that you have values. Now this gk will increase to the function g. I guess I want to call it little g. I don't know, whatever. Which is the same thing, except now the sum goes out to infinity. What can we say about g? G is in L1. But G is in L1 since the integral of G is already non-negative. The integral of G is equal to the integral of fn1 plus the sum of all of these as k goes from 1 to infinity, fnk plus 1 minus fnk. And we made these differences, you can almost see it, we made these differences have L1 norm at most 1 over 2 to the k. This is at most 1 over 2 to the k. This is finite, n1 is, fn1 is L1. This sum converges, this converges. Question?
So why is G equal to this infinite sum? Or why is integral of G equal to this infinite sum?
Oh, so G itself is equal to, so infinite sums of positive, non-negative things can be pulled past, where was this? On the first page.
I think we did this last. Okay. I believe it.
Infinite sums of non-negative things can be interchanged with integrals. Okay, so infinite sums can be interchanged with integrals. Integrals are linear. So the GK converge up to G. By dominated convergence, the integrals of the GKs converge up to G. So what do I want to say? The G being in L1, here's what I want to say. G being in L1 means in particular that G takes the value infinity on a set of measure 0, which implies G equals infinity on a set. So G is less than infinity almost everywhere. That's a better way of saying it. So G being finite almost everywhere means this series converges absolutely almost everywhere. Which means the series defining F converges almost everywhere. In other words, the Fk converges to F almost everywhere. Which implies the series defining F converges absolutely almost everywhere. G can't take the value infinity with a positive measure. G is the limit of these partial sums. So these partial sums can't go off to infinity infinitely often. In other words, these sums are absolutely convergent for all but a set of measure 0. Okay? But the series defining F converging almost everywhere is the same thing as saying the series defining F is Fk. The partial series is Fk, which is Fnk converges to F almost everywhere. Does that make sense? So we went from not knowing where to look for a function. We cooked up this function. We didn't know, like, where are you supposed to find your function that things converge to? Well, we wrote down a function. And in fact, that function is the pointwise limit of these fnks that have been sped up sufficiently by taking a subsequence, by this process. And now we can apply the dominated convergence theorem. So note that f of x, so whenever this f of x exists, I can say f of x minus f and k of x. So what is this? Right, this was the initial segment, so this is the final segment. It's the tail. So this is, well, let's say this is equal to the tail, so this is as k goes from big K to infinity of f n k plus 1 minus f n k. Sorry. Anyway, I'm running out of room. Now, triangle inequality, this is at most the sum as k goes from k to infinity of f n k plus 1 minus f n k. But that tail is a piece of what's inside G. So this is bounded by G. And G is in L1. So we have this series of measurable functions which are bounded by this L1 function, dominated convergence. So dominated convergence now. Dominated convergence implies what? In L1. So this converges, this difference converges almost everywhere to 0. And dominated convergence says when you have fnks converging to f, or if you have some function that's converging to another function and that function is dominated by an integral of a function, then the integrals converge. Then it converges in L1. It bootstraps almost every to L1. That's exactly what we want, which implies in L1, this is going to 0.
Can you say again why f n k converges to f almost everywhere?
Yes, so fnk, let me slide things down just a little bit. The reason, so let's look at the argument. So G is finite almost everywhere because it's L1. G is this sum. So this sum converging almost everywhere means that the fk's, means that the series defining f converges almost everywhere. Which means that the fk's, which are the partial series, converge to f almost everywhere.
Why? Because their difference is close to 0 or what?
Yeah, so another way of looking at it is this, right? If that series converges, then it converges because the partial sums converge to the infinite sum.
Yeah, okay, gotcha.
And what is the partial sum? It's the fnk.
Thank you.
So that's this telescoping argument. And so the last step is we have this G that dominates everybody. Because we've sped things up sufficiently, we have this integrable G that dominates everybody, and so we have L1 convergence along this subsequence. And now when you have a Cauchy sequence, let's finish it. We're almost at the end. So here's an easy corollary, easy finish. So let's say epsilon is bigger than 0. Let n be such that for all n and m greater than n, fn minus fm is at most epsilon. So we're back to our original, the entire Cauchy sequence. Let's make that epsilon over 2. And now choose k large enough that, first of all, f minus fnk is also at most epsilon over 2, and nk is bigger than n. Okay? So I know that what I'm starting with is a Cauchy sequence. I know that there's some subsequence along which it converges. So given an epsilon, I can take some n, where the Cauchy sequence itself is at most epsilon over 2, and then I'll take an nk bigger than n in my subsequence, in my special subsequence, which is also within, so by making it large enough, I can make it within epsilon over 2 of f, and I can make it bigger than capital N. Then we're done. Then the distance from the sequence itself to f is at most the distance to nk plus the distance from f to nk, the triangle inequality. N and nk are both greater than capital N, so we're in this position, this by assumption is at most epsilon over 2. So we found a limit. Okay. It's worthwhile here to record. Yeah. Okay, let me just record one immediate corollary of the argument, not of the theorem, but of the argument, which is that this counterexample doesn't happen along subsequences. So what we really proved, corollary of the proof. Okay, so before I do that, let me pause for a second just to see that everybody followed. Let's review this argument. This is a deep theorem, the Reisz-Fischer theorem, the completeness in the L1 metric of the L1 space. Okay, what did we do? How are you supposed to find? When you start, the hardest thing about this, for me at least, the hardest thing about this is you have these sequence of functions. How do you get going? You don't know that they converge anywhere, right? You can't just say, well, take their limit. What limit? First of all, they don't have L1 values, so you can't even take a limit. And I don't have a good target. So the first thing we do is we speed up the subsequence to have L1 norm at most 1 over 2 to the k. So we just take the first guy, the first f and k for which after that this is true, and we pull that out as our subsequence. Then we set up this telescoping thing. And it's clear that what we're really doing is taking the limit as k goes to infinity of these f and k's, at least if you write it out in this telescoping way. We observe that in absolute value, by construction, this has been made to have finite L1 norm. And then we use dominated convergence to get from almost everywhere to L1. Okay, so dominated convergence upgrades almost everywhere convergence to L1 convergence. This is trying to go sort of backwards. I mean, we've cooked up this function, and then we have to show that the L1 convergence. It's not backwards. It's still the same direction. Okay, is that clear? This is like a really good use of all of these analytic tools.
Small questions.
Yes.
Why would let f be formulated like that?
Why did we start with f being this formula?
Yes.
I don't know what the original proof of this was, but it's a clever device which is an upgrade of this. Sorry?
Which is convenient for our proof.
Well, it's a useful device to keep in mind. If you're trying to get something to converge, you want to get it to converge by breaking up. This is very similar actually when we have like a union of sets, and then we break the union of sets into disjoint pieces. Yeah. It's very reminiscent of that. This is like taking the set difference, right? You have E1, and then you have these set differences that are each of which is small. So the smallness is what we're going to try to exploit. The smallness of each of these differences in L1 is what we're going to exploit, and then with triangle inequality we can add them all up and get something done. Okay, so that's kind of the trick of this. And you can only do it along a subsequence, and let's just record that fact. So corollary, not of the statement but of the proof, is that if Fn is any sequence in L1, and Fn goes to F in L1, so it is certainly not true, not true that Fn goes to F almost everywhere, as we saw in our counterexample, but there does always exist a subsequence along which we do have almost everywhere convergence.
And we can just take the subsequence from the proof, right?
Exactly. And the proof is exactly what we did. You cook up. So if you have convergence, then you cook up this kind of thing. Just skip until you're at least within 1 over 2 to the k of f. Just speed it up. Okay. Yeah. We'll start the next bit next time. Any questions?
This can be done for any convergent sum. Like one instead of 1/2k, 1/k squared.
Yeah, any convergent sum. Yeah. The fact that this, all we used about 1/2 to the k is that the series 1/2 to the k converges. Wherever this is. All we used about this series is that it converges. And 1/2 to the k adds up to 1. Good. Okay. See you Friday. We'll start.